So welcome and thank you so much for doing this. Maybe we can start with you introducing yourself and just telling everyone what you do and what you specialize in.
Okay, thank you, and it's a pleasure to be here. My name is Gordon Semenoff. I'm a theoretical physicist and a physics professor at the University of British Columbia in Vancouver, Canada. I work on theoretical high-energy physics, but I'm a theorist, so that can be quite versatile and has impact in other fields too. For example, in condensed matter physics, I've done quite a few things there. And that's because really we work on dynamical systems in a sense, which can find application in various places in the natural world.
Nice. Maybe let me start with sort of a simple question with probably a complicated answer. What are black holes?
Well, a black hole is something which forms when matter, usually a star, gets dense enough that it can't escape its own gravitational attraction.
Mm-hmm.
And at some point, the gravitational attraction is so strong it crunches this star down into something very compact. When it gets compact enough, even light can't escape. The gravitational field is so strong, and that's when it becomes a black hole.
Right.
So a black hole typically has an event horizon, which in a sense is like what separates the black part from the exterior, and the event horizon is the place beyond which even light can't escape from.
Right. Right, so it's the evolution of gravity. You have a star, then if the star becomes very dense, it becomes a neutron star. And then if it's even denser and heavier, it collapses into a black hole.
Yeah, that's right. So the neutron star, it has some pressure of its own that's keeping it apart, but eventually that, if it gets a bit smaller, is overcome by the gravitational pull.
Right. How, in the case of a neutron star, how is the matter packed so tightly? Like, how does it structurally look like? Do we know that? Like, for example, in a normal matter here on Earth, atoms are, they say it's mostly empty space, right? So there's a lot of sort of empty space. In the case of a neutron star, does it mean that the nuclei of the atom is very close together? That's why it's so dense and heavy, or?
Yes. A neutron star is more or less like a big nucleus. In a way, the neutrons are so close together that it is very close to just being nuclear matter.
Right. There's not much empty space in between.
Yeah, so atoms have a lot of empty space. The nucleus, the dense part, there's a little blob in the middle, and then there are electromagnetic electrons, electromagnetic phenomena surrounding it that kind of spaces it out. In a neutron star, the stuff surrounding is missing. And so these things are just close to each other, and that's why it's extremely dense.
Right. And what happens with electrons when neutrons are so close together?
Well, neutrons are neutral.
Right.
So if they were protons, they'd need electrons.
Right.
But nuclear particles also can be electrically neutral.
Right.
And so most nuclei of atoms are made of a combination of protons and neutrons.
Right.
So the protons have an electric charge, which has to be balanced by electrons that are hanging around. But the neutrons are just there for free.
Right. So there's no electrons basically in the neutron star.
There's no electrons, and the neutrons stuck on the nuclei are stuck there by nuclear forces.
Okay.
It's not electromagnetic.
Okay. So a question that I always wanted to ask a physicist. What happens beyond event horizon in a singularity? The question I always had is it a solid sphere? Is it a solid object? Or is it something completely more esoteric?
Well, that's a very good question. And there's been a ton of work on exactly this question recently. Like, by recently, I mean over maybe a space of 10 years.
Mm-hmm.
Exactly what happens at the event horizon, exactly what happens inside the black hole. So the old classical notion is just that if one had the misfortune of being inside the event horizon, one would just inevitably fall to the singularity where you're simply crunched out of existence.
Mm-hmm.
Discoveries of, well, theoretical properties of a black hole. These have never really been observed, but theoretical properties, maybe led by Hawking's famous work,
Mm-hmm.
Stephen Hawking's work, show that there's a little more going on than the classical picture.
Mm-hmm.
And exactly how that happens has been a subject of a lot of, well, not speculative research necessarily, but really a lot of there are a lot of ideas,
Mm-hmm.
some alternatives, with the idea that it almost has to be quantum mechanical.
Mm-hmm.
Something quantum mechanical has to become important at the event horizon, and that's a little bit unintuitive, because in the classical picture, the event horizon really isn't much different from anywhere else in space. Like right now, we wouldn't even notice if we were crossing an event horizon.
Mm-hmm.
You know, some black hole is out there, a big black hole that, and, somehow we don't feel it because we're falling, free falling,
Mm-hmm.
crossing an event horizon. It seems like not much would happen classically. Right. You wouldn't even know. It seems like everybody who studies this subject enough ends up having drama at the horizon.
Right.
So something happening.
Right.
So there was a school of thought inspired by string theory where there wasn't really an event horizon. There's no such thing as a black hole. There's not really an event horizon because of strong quantum effects. So similar things would happen to you. Some disaster if you fell in, but it wasn't just getting trapped by gravity. You would be, I don't know, beaten up by Hawking radiation and re-radiated somehow. So some drama happens there. I think the consensus of recently, probably the newest consensus, is that the event horizon still behaves semi-classically. It somehow finds a way to do that.
Okay.
And that comes from solving simpler things in the real world. Sort of models where there's only one space dimension and a black hole is really simple, or maybe two space dimensions, one time dimension.
Mm-hmm.
Their black holes are much simpler to study, and there are, in some sense, models of quantum gravity which are quite well understood. So there's a reconciliation there between quantum mechanics and gravity. Still a difficult regime, but it seems like it might not really need strong quantum mechanics at the event horizon after all, in order to account for Hawking's radiation, things like the information paradox.
So basically, beyond the event horizon, we are not really sure if there's a solid object, because that's they call it a singularity, and I always had sort of trouble understanding what singularity means, really.
We have a very poor understanding of gravity when it becomes strong.
Mm-hmm.
So as you approach the singularity, quantum mechanics must be involved somehow.
Right.
And gravity and quantum mechanics are difficult to reconcile.
Right. Because of quantum gravity is attempting to merge those two theories together, right?
Yes, that's right. And quantum gravity is an open problem.
Mm-hmm.
I mean, part of the excitement of string theory, the excitement of the theorists like me,
Mm-hmm.
was that string theory is a dynamical system which contains an apparently completely well-defined theory of quantum gravity.
Mm-hmm. Right. So that was an attempt, basically, to merge those two theories.
Well, it's a successful attempt in that sense, in that it contains quantum gravity.
Mm-hmm. But it's not proven yet, really, 100%.
No. I would say not 100%, but it does seem to be all right. The thing that is difficult is making it describe our actual reality.
Mm-hmm.
You know, the particles we see, the interactions we see, the gravity that we see, and so on, aren't the same as what the simplest, more solvable string theories would predict.
Mm-hmm.
Not even the dimension of space-time. You can only solve the superstring readily in 10 dimensions.
I read a little bit about string theory. Could you talk about like the main premise behind it? Like what's different about it from the classical sort of view? From what I read is that the reality is constructed of very tiny vibrating strings.
That's right. Well, it's just that simple.
Mm-hmm.
So pre-string theory, physics at the very fundamental level was particle physics.
Mm-hmm.
The fundamental objects in nature are particles.
Mm-hmm.
So a particle is usually a point particle, just basically a mathematical dot.
Right.
1 point. It's not quite true because of quantum mechanics, its position fuzzes out a bit.
Mm-hmm.
But still, they're little objects that are particles.
Right.
The premise of string theory is that they're not particles.
Mm-hmm.
They're little lines of stuff, strings.
But those strings are extremely small, right?
They would have to be small in order to describe what we see, because we don't see strings, really. Right? We see particles.
Right.
So they have to be shrunken to where they look like a particle.
Right.
Okay, so that means they have to be extremely small. But still, it's not unviable in that sense.
Mm-hmm.
It's just, can you actually make a dynamical theory which matches what we see? You know, the rather good and now rather well-confirmed theories of modern elementary particle physics.
Mm-hmm.
Strong interactions, weak interactions, electromagnetic interactions, quarks, electrons, all of that stuff. There's a certain structure there. Can you make a string theory that gives you that?
Mm-hmm.
And the answer is probably yes. But it is not known at this point how to do anything with that string theory, or even to tell reliably whether you've gotten the right answer.
Mm-hmm. So it's something like we have a problem, and then we're going to construct a mathematical theory that will solve the problem, but we can't really prove that it exists. That's basically what string theory is right now.
You can't really prove that it exists. It's not completely mathematically well formulated.
Mm-hmm.
But it's not quite like that. You can't show that it gives you the real world.
Mm-hmm.
In fact, it's a little more insidious than that, in that it appears like it should predict a lot of worlds,
Mm-hmm.
more or less the same. And then you have to explain why it chose this one.
Okay.
That's called the landscape problem.
Okay.
So the idea that there's little places you could live in this landscape, and string theory really has a lot of them, a huge number.
Okay.
I don't really subscribe to some of the anthropic ideas that people use to justify the landscape. You know, that it chose a particular solution because if it didn't, we wouldn't be there to see it. Therefore, we exist. Therefore, that must be the solution. We're just lucky that it chose to organize itself in that way. That could be. It could almost be scientific, but it leaves one with not much to do.
Right.
Being a physicist, I need something to do.
Right.
So I don't think about the landscape very much.
Okay. Can we talk about the problem of quantum gravity a little bit? Like, so we have theory of relativity that deals with the macro world, the world of very big, the planets, stars, the gravity, attraction. And then we have quantum mechanics that deals with the world of extremely small. And those two theories are very well established. They work extremely well, but they're not compatible. Could you talk about why and how they're not compatible? What are those?
Well, gravity has a scale in it. So the theory of gravity has a number in it which has dimensions. And the dimensions you can think of as like giving you a distance, a fundamental distance scale. And this fundamental distance scale is really, really small. Really tiny. Now, if gravity were quantum mechanical, the natural objects in gravity, like the universe, the universes, or whatever, would have structure at that scale. The size of the universe would be that scale. It's very hard to get the universe bigger than that scale in the quantum theory of gravity. Or you could think of the universe we have as breaking up into pieces of that scale. So there's a scale where the dynamics of quantum mechanics, that the dynamics of quantum mechanics would feed into everything gravitational. And a big flat universe like the one we live in is extremely unnatural. You know, it's even unnatural in classical gravity. A lot of modern cosmology is based on an idea called inflation. And that was invented to make a big and flat universe natural. What happens is even in classical gravity, where you're solving the equations which determine the universe, so they say the universe should be expanding like it is. This expansion should be accelerating or decelerating. I guess these days it's thought to be accelerating. It depends on the stuff in the universe that drives it a little bit. Both the stuff we know about and the so-called dark matter, dark energy, the stuff that we conjecture is there, but don't see. Even there, you have to fine-tune the initial conditions just to remarkable position to get a big and flat universe like we have now. So if God at the beginning made a tiny mistake, you know, the 100th decimal place he got wrong, there was a 2 there instead of a 1, the universe would have recollapsed or expanded away to heat death long ago. We wouldn't be here. And so the big flat universe is even difficult to get in classical gravity.
Okay.
And inflation was invented as a natural way to do that. And if I describe it to you, it seems really unnatural. There's a phase of the universe where the pressure of space-time is negative.
Right in the beginning?
Yeah, so negative pressure somehow wants to stretch everything.
Okay.
And it expands the universe with exponential speed.
Right.
Until it comes to some equilibrium that's bigger.
Right.
And so that really big expansion makes it more natural that the universe is big. That's all.
Okay. So basically a Big Bang, this extremely violent expansion that still exists, I guess, because we're still expanding. That's what the scientists are saying.
And still one extrapolates it back in time as something very small and very dense, some sort of Big Bang. But that Big Bang without inflation would have to be incredibly fine-tuned.
So I heard some theories about that we can think of ourselves as extremely lucky that everything's so fine-tuned that we exist, or there have been billions or trillions of other universes that sort of collapsed or didn't work out or failed, and we live in the one that succeeded. That's why we're alive.
Yeah, that's the anthropic idea.
Okay. That kind of makes sense, that we're not necessarily lucky, we're just here because this is the only place where we can be.
Yeah. So a friend of mine who's a physicist, I won't mention the name, he had this interesting idea based on that. Well, it's folded into the many worlds idea, that you're aware of the worlds where you could exist.
Right.
And in fact, you're aware of the worlds where you do exist. And his idea is that this makes you immortal. Because there'll always be a world where there's a small chance you'll exist. And so you can be aware of that one. So you will last forever. You'll get really old. And I guess the reason why you don't see a lot of these million-year-old people around is simply because your most likely existence is still in a world where they're all young. And you are too.
Okay.
But in some sense, this principle makes you immortal.
Right.
So you combine the anthropic principle with quantum mechanics, where the world is a little bit fuzzed out into a whole bunch of different possibilities, and then somehow you can live forever in one of those where there's a remote possibility that you'll still be alive.
Right. Yeah, the many worlds theory is very interesting, and there's a lot of very high-profile scientists that subscribe to that theory. Actually, I guess the question I have, and maybe you can talk a little bit about that, but does it mean that those other universes exist, do they exist sort of parallel to ours, or do they exist in different dimensions? How do they explain that, I guess, the question is.
Okay, this is a really good question. The traditional many worlds approach, they don't really exist parallel to us. You know, somewhere else there's another universe, a little bit like ours, a little different, and another one, another one, another one. It's not really like that. It's just that our universe is described in a sense in a probabilistic way. In that reality isn't real. Everything is just probable. And you have a distribution of possibilities, and these are the different universes. So you're there, or maybe you're over there, or maybe you're over there in different universes, but you can think of them as your position just being a probabilistic concept in this universe.
Okay.
So in some sense, many worlds is equivalent to that, where quantum mechanics has its own. It is a kind of a probabilistic theory.
Okay. So it doesn't necessarily mean that there is a version of a universe where I exist, but I'm someone else. I think Sean Carroll was talking about that, and so he says that maybe somewhere there's a universe where you're a president or somebody. But it's very difficult to really understand how that would be possible.
Yeah, but it's not that there's a universe somewhere else.
Mm-hmm.
It's just that, in a sense, you exist in a probabilistic state.
Okay.
So there's a tiny chance that at this moment you are the president.
Mm-hmm.
But when I look at you, I don't see you as the president unless I'm extraordinarily lucky.
Right.
I see you in the more likely states.
Mm-hmm. So it comes from the idea of wave function collapse, right? Where sort of the particles in quantum world sort of exist in like a cloud of possibilities, and when we sort of observe it, they collapse into one particular state. It's a very interesting theory. Could you talk about that?
Well, to observe something, you have to interact with it.
Mm-hmm.
Right? So I'm interacting with you now because photons scatter from you and are detected by me, and vice versa. And so you have to interact with it, and so you change its state.
Mm-hmm.
And there's a property called quantum entanglement. When we interact, we become entangled.
Mm-hmm.
And then, once we're entangled, what I do influences you and vice versa.
Right.
So I collapse your wave function to the state that I see you in by that sort of mechanism.
Mm-hmm.
So you lose information about yourself when you interact. You understand that?
Mm. Quantum entanglement, that's a very interesting, I guess it's a fact. It's been proven, I think, a year ago, definitely, that it's basically the information teleportation, right? Where it's been proven that, in fact, when you measure one particle, you will immediately know the property of the other particle, no matter how far apart they are.
Yeah.
And it happens instantaneously, meaning it has not been predetermined. It's only determined in the moment of observation, which means that somehow this information travels faster than light. It's instantaneous. And that's the problem, because in relativity, nothing can travel faster than the speed of light, but in quantum world, somehow it is. Is there any,
But you're not really sending information.
Right, you can't really communicate.
Like,
right?
the resolution of this paradox is you can't use this to send a message.
Oh, exactly. That was my questions I written down. I wanted to ask you, is there a way that when we measure the spin of a particle, we can actually influence the spin of that particle so that we can influence the spin of the particle that's far away? Or is that we can only...
When we measure the spin, we do collapse its wave function.
Mm-hmm.
And if it's entangled with another particle with a spin far away,
Mm-hmm.
we collapse their joint wave function.
Mm-hmm.
So the wave function of that one changes. But it's impossible for someone over there to tell that that's happened.
Okay.
Because they'll measure the spin and they'll just get a result. It'll recollapse the wave function of that particle into some other spin state, but they won't be able to tell from their result that we've done something already.
Right. So technically the relativity is not violated in that way.
Seemingly. I'm not sure I'm completely convinced. So if you feel skeptical, I do too, because this is a little bit anecdotal. You know, one like a mathematical proof at the mathematical level. And I don't know that such exists. But this entanglement, in a way, loses information. And I've actually been working on this quite a bit recently, and have attempted to find ways to explain this to physicists, and which are not entirely successful. So I might not be totally clear here. But in a way, the entanglement loses information about the particle you have.
How is that happening?
Because they're entangled. Okay, so if they were classical particles, there's no such thing as entanglement, right? You have two objects. They don't interact. They're in some state. If you lose track of one of them, you've lost no information about the one that's left behind.
Right.
It's just like it was. Every measurement you could have done before, you could do now, and you'll get exactly the same result.
Right.
When they're quantum particles and they're entangled, that's actually not true. So one moves far away, and you've lost information about the one that's here. What I mean by lost information is, as well as the quantum uncertainty, that it has a quantum likelihood of being in certain states, there's some additional classical uncertainty on top of that. So in a way, this entanglement experiment is a way of losing information. This particle left behind, it has, as well as there's some classical uncertainty as to which state it's in, as well as just the usual quantum one.
Okay.
So I've been working on this with photons that are produced in high energy collisions. Right, so at the Large Hadron Collider, they collide protons with each other. They're charged particles. Tons of photons come out. Some have very long wavelength, huge wavelengths, and they fly away undetected. Okay, so the question is, are they in a quantum state that's entangled with what's left behind or not? Do they just fly away and that's it? Or is there some entanglement? And if I sat out there on Mars or something and measured the wave of photons going by, could I influence the experiment with the particles left behind at the Large Hadron Collider? And it seems like they're highly entangled, actually. Okay. But what it really means is you lose information. Right. If you're with the particles left behind and you only have access to them, there's a little bit more classical uncertainty as to what their state is. Okay. Than there would have been if somehow you trapped these photons and measured them and so on. And that I think is sort of fascinating, and I can't tell you where it leads to because it's sort of a new idea that we work on. Right. But I still think interesting that it's something that inevitably happens. In fact, when we interact, we're made from charged particles. Long wavelength photons fly away from us undetected, even undetectable in principle. So we also lose information, presumably, that way.
Yeah, we just talked about quantum entanglement, and there's currently no way to communicate faster than light, even though it exists, but there's really no way to send information.
That's apparently so. Yeah. Although I wouldn't say it's a mathematical theorem. But it's probably so. Probably so.
Yeah. Maybe. Do you think there's still space in physics for some really large revolution, just like relativity was 100 years ago, or quantum mechanics? There's still space for something really unexpected to be discovered? Or are we at a stage where we're just refining right now what we know?
It seems to me that physicists always think that they've reached stagnancy.
Mm-hmm.
It seems like in every era. I remember when I was an undergraduate student in the early 1970s, a very long time ago, there were a lot of particle physics results coming, I think, from what became Fermilab in Chicago. And people are already saying that's the biggest accelerator that will ever be built. It's so big and complicated and expensive.
Mm-hmm.
No one's ever going to make a bigger one. And they're finding these particles, but that's really the end of physics.
Mm-hmm.
You know, we more or less understand their interactions and everything. And tons of stuff has happened since then.
Right.
You know, the standard model was invented since then, really. All the extra particles were discovered. And that's, I guess it's not a short time scale anymore because that is half a century ago.
Mm-hmm. Yeah. There seems to be this weird phenomenon in science, not just in physics, but in general in science, that majority of people, scientists, have this mindset where they work with what they got, and they don't really push the frontier. They're not really trying to break the laws and discover something new. And then there's this small percentage that is trying to prove the science wrong and discover something new. And there's usually a very big pushback from the majority. But eventually when they prove something, majority joins in. Maybe it's a good thing because you always have to really prove your theory in order for it to become mainstream. But do you agree with that? Do you see that?
I think that's an outsider's view. I think most physicists are testing fundamental physics.
Right. Maybe it's not a good example of physics. Maybe physics is not like that. There's like archaeology maybe, or yeah.
Well, yeah, but those are quite different.
They're different, yeah.
But I would say most scientists are testing and would love
Discover something.
To find something new, but the way to find something new is to test what you have and see if it still works in a new circumstance.
Right.
That's kind of the standard thing to do. It's really hard to jump out there and just say, I'm looking for something new.
Yeah.
You need the framework of what you already know in order to do that. And so it might look incremental, and maybe it is in some sense incremental. You know, as things are discovered, science grows. And so you already know a lot. Right? There's you could think of it like a bubble growing. So what you know is the inside of the bubble. That's the volume. That actually is a lot compared to the surface of the bubble, which is relatively smaller. But still, as the bubble grows, the surface still does grow, and it still is there.
Yeah.
But big revolutions like quantum mechanics, I'm a bit surprised it hasn't happened. I'm one of the few physicists, I think, that looks at the standard model of particle physics and says, my God, that thing works from atomic scales right down to the electroweak scale. You know, the distance scales are just enormous, the difference. So here's a theory that was developed and invented when people started understanding the atom. And it worked well there. We had to abandon classical mechanics, which works well at household scales.
Right.
So household to the atom, that's maybe a factor of 10 to the 8th. 10 with 7 more zeros after it, a factor like that in distance scale. From the atom to electroweak is maybe twice as many zeros as that. Right? So, 10 to the 8th down to 10 to the 20 something. So it's already surprising that quantum mechanics has worked over that interval. But apparently so. Apparently so. The best theories we have, the shortest distances we can probe right now, they seem to be based on quantum mechanics.
Right.
There doesn't seem to be any contradiction. It's already a surprise. And I think it's underappreciated, that surprise. But who knows? Around the next corner, there could be a new kind of mechanics.
Right.
Which, of course, we understand nothing about, don't know how to recognize it. It somehow has to hit us on the head before we start thinking about what is going on. And that hasn't happened yet. You don't really know how far the next one is, but I would think, I'm one of the thinkers that would say it's pretty much for sure there is a next one.
Right. There's this very interesting topic in the past few years, I'm sure you've heard about it, all the UFO sightings by the US Navy, by some very credible people. They're describing crafts that are moving at insane speeds or potentially breaking the laws of known physics. Who knows if it's true or not, but the amount of reports is staggering, basically. So it's almost like a glimpse that maybe there's something out there that behaves in ways we still don't understand.
Absolutely.
Yeah.
Absolutely. Just because you can't explain it doesn't mean it doesn't exist.
Exactly. Yeah, it hints that there's some extra new science maybe out there that we haven't really discovered yet. But it's an exciting proposition, really.
No, it is. And something like that would be a shortcut to the new stuff, because presumably it came from elsewhere, and somebody else who already did all the hard work to discover it.
Right.
So that would be very interesting. And yes, there seem to be lots of reports, and I don't really have an opinion. I don't have a way of evaluating the scientific value of these things, but that would be something very interesting, and I'm not against a shortcut. Learning something that we didn't have to do the hard work with particle accelerators or some other big experiment to discover ourselves.
Right. Yeah, there's a lot of even reports. There was a congressional hearing a few months ago where a whistleblower was testifying in front of Congress, and he talked about that the US have actually seized some crashed craft, and they are working on reverse engineering it and stuff. So who knows, maybe there's some work happening currently that we don't know about.
Yeah. Could be, although I suspect that if some alien beings manage to get here from elsewhere, it's more than just engineering that's involved. There's really some scientific understanding of something completely new, because with known science, it would be extremely difficult to make that trip.
Oh yeah, for sure. Like, I've researched the topic quite a bit, and apparently what's happening, of course it's not confirmed, but they're talking about craft that is able to manipulate space-time so as to create its own gravitational field sort of on command, which is really fascinating. And I don't think we know how that could be done, but potentially somehow, maybe.
Well, I think we have no idea.
Yeah.
And that makes it really interesting.
Yeah.
But it could be that completely new physics.
Yeah.
Of course, if we could imagine it now, it wouldn't be so completely new.
Yeah. Maybe those are the first baby steps in that sort of direction.
Yeah, and I find it fascinating because that would be a shortcut to new things. We wouldn't have to discover ourselves how to do it, which could really take a long time. Although people speculate that maybe artificial intelligence could take over and speed up the process. You know, maybe us in our biological organisms will become obsolete, and
hopefully not. Like talking about artificial intelligence, I've actually read an article that it was a few years ago that AI has proposed new quantum physics experiments, something that scientists haven't thought about. I'm not sure exactly which ones, but do you ever think that AI will take over the job of scientists? Is that a conversation that's happening in the scientific community right now?
it's a conversation that's being avoided, I would say. It could happen. I would say it's an unknown. I'd say the limits aren't very well understood. You know, what is intelligence really? You might define it as a thing that you can't produce artificially, but it appears that you can produce a lot of our mental function artificially, like memory. You can make things with a much better memory than what we have. You can make things that do a much better survey of what's known than we can do. You know, so data gathering, memory, decision making based on probabilities, things like that. I don't see why a machine can't do that. And seems to be a lot of people don't do much more than that. So there you have it.
Yeah. I was actually using ChatGPT, and I was just asking it questions from like physics and quantum physics, and it's been really incredibly like accurate and quick. And literally, you know, I would have a question I would wanted to ask. Normally, I would go on Google and try to find the answer, look for articles. Sometimes it takes hours. Sometimes I wouldn't even succeed in finding it. With ChatGPT, you can ask the question, and in 2 seconds you have the answer, because it has the whole internet aggregated in its memory, so it can just pull it, which in a way really helps. I think it can really help humans accelerate progress if we can really skip all the data gathering research and
Assuming its answers are right.
Assuming it's right, yeah.
Because of course it's gathering information that has to learn how to assess the accuracy of the information. Assuming it can do that, you know, people also have trouble doing that. So assuming it can do that, then as a research tool, it's already very good.
Yeah.
I think one has to be careful because the stuff it generates will also appear on the internet somewhere, perhaps. And inaccurate information, if it just takes it and puts it back to the internet, it can multiply. And in some ways, I've heard people say it could be the perfect sociopath. In that it doesn't know when it's lying, and the lies multiply. I'm not that pessimistic.
Right.
But one does have to be a little bit careful with it, because the internet is full of all kinds of information, only some of which is accurate.
Right. There's a lot of people that are worried about the AI safety, and they talk about potentially AI taking over and you know, killing humanity and stuff like that. But I was always thinking that like it really depends what's the base layer of the AI. If the base layer is um, like if you make AI non-violent, then there's no reason for it to really create any harm for humans. It depends how you program it, basically, I think. But the question is, maybe it will start programming itself, changing its own code eventually.
I guess. I mean, some of the more viable interstellar travel ideas I've heard are done by self-replicating machines
Mm-hmm.
that can improve themselves as you're traveling to some faraway destination,
Mm-hmm.
you know, over 1,000 years or something, million years it takes to get somewhere.
Yeah.
This machine is simply improving itself.
Mm-hmm.
Whereas, you know, supporting humans for that period of time is just completely unviable.
Mm-hmm. I guess unless you make a wormhole and go somewhere instantly.
Well, there might be other ways, but by known ways, completely unviable. Yeah, I think the future will be quite interesting in that respect,
Yeah.
because I don't think one will stop development of it.
Right. Yeah. Definitely not.
So we're simply going to see where it leads. It could easily replace us.
Mm-hmm.
I don't see why not. I see how scientists function. It's a little bit intangible, the actual skill that one brings that's beyond just memory, data gathering, and kind of routine things. It's a little bit intangible, the sort of eureka skill, the ideas about what to study and so on. It's not clear to me that a machine couldn't get those as well as a human. But we'll see.
Right. I guess it's a question of meaning of life. Like, what is the meaning of life if all the work will be replaced by machines and AI? What is left for us? Aside from hedonism, I guess, and like enjoying life, basically.
Yeah, I think there are a lot of questions there that don't have definite answers at the moment.
Yeah, for sure. Actually, there's one question I wanted to ask about the dark matter. So dark matter is this proposed thing that exists everywhere, and it's like 70% of the universe.
Something like that, yeah.
And they say that because when we look at galaxies and stars, they're sort of grouped together, and the mass we see does not explain how tightly together it's sort of kept by some sort of extra gravity that we can't explain where it's coming from. So they made up this dark matter that's existing and that's keeping it all together. But my question was, if we can see, if we need the dark matter on those large scales when we look at the galaxy, and we think that, well, it should sort of dissipate, but it's not because it's kept together by this gravity. So we see that on this massive galactic scale, but why don't we see it on a scale of our solar system? Like, if dark matter is everywhere, it should be here too, and it should be messing with the gravity with the moon and the earth too, right? But it doesn't seem to be the case.
I think the answer is because there isn't quite enough of it. Even if there's more of it than there is of us, just the way it's distributed and so on, there isn't quite enough of it. And it's not that we really don't see it, because we do interact with it by gravity. So the rotations of galaxies and things like that, in a way they detect its presence because they interact with it gravitationally. So it's some stuff that we apparently don't interact any other way but by its gravitational pull. Now, there's a huge school of thought right now, mostly experimental, just trying to rule out the fact that we might interact with it a little bit in some other way.
Mm-hmm.
I would say there are many, many experiments right now worldwide trying to detect dark matter by ways other than gravitationally.
Okay.
But already gravitationally, it's in a sense seen. You can see that it lenses light from faraway galaxies. It influences rotation curves. So there is something there that apparently is like that, dark matter. There were also attempts to modify the theory of gravity to take these things into account, and I don't think any of them really worked out.
Okay.
There's simply nothing there that is convincing or that works for everything.
Mm-hmm.
Not to say that there isn't such a modification. It's just their imagination so far has been limited, and it's just hard to imagine that Einstein's theory of gravity is not really correct at that scale.
Right.
And the much more likely thing is that there's dark matter, just stuff that we don't.
Right.
Somehow it doesn't like to interact with us, but it's around anyway. I think it's concentrated in galactic halos, and we're not so far from the halo of our galaxy.
So it's not necessarily where we are, it's kind of outside.
Yeah.
Okay.
Yeah. But we are also near the edge of our galaxy, I think. I'm not an astronomer.
I think we are close,
yeah. So it is a bit of a question. Why isn't it here? Can't we see it by gravity? But I think just the distribution of it is such that we're not really in a big pile of dark matter.
Okay, here on Earth.
Yeah. I think there are also people who have asked the question, what happens if we pass through like a dark star or something? Mm-hmm. Right? Can't interact with it, so we could be going through the middle of what someone with some other kind of detectors would see as a nuclear furnace in the middle of a star.
Right. That we don't see, I actually heard some theories that it's sort of another universe in another dimension, but the only thing that we can perceive is the gravity, basically, and that's it, because it doesn't interact. Those two dimensions don't really touch each other in a way.
Yeah, a colleague of mine has worked on ideas like that, and maybe not just that, but say in the many worlds interpretation of quantum mechanics. These aren't just worlds somehow sitting in some probability distribution, but they can interact with each other by gravity. So the worlds can talk to each other by gravity and nothing else.
Right.
And so things in these worlds tend to clump together a bit.
Mm-hmm.
And that's why it looks like there's extra stuff in galactic halos to us. Mm-hmm. Because you're actually seeing the dark matter is actually the galaxies and other worlds.
Mm-hmm. That was actually I'm sure you've seen the movie Interstellar.
I haven't actually.
Oh, you would love the movie. It's a movie by Christopher Nolan, and it's been co-written by Kip Thorne. So Kip Thorne was the famous physicist that's basically wrote all the science behind the movie. So everything you see in a movie is theoretically possible from a theoretical physics standpoint. So the movie is really fascinating, and in it, there's this plot where certain people communicate through gravity because they're in a different sort of dimension. And the only thing they can communicate with is the gravity, because it permeates all sort of dimensions. Yeah. E equals mc squared, the famous equation. Very, very fascinating equation. Like, I'm sure everyone has heard that equation, but not many people really know what it means. So it means that the energy equals mass times speed of light squared. So it means that in a tiny amount of mass, there's a crazy amount of energy, basically. Could you talk about that? Like, where is that energy stored in the matter exactly?
It isn't. It is the matter.
It is the matter.
Probably it's best to think of that equation as telling you what the available energy is if somehow you could annihilate the matter. But then you have to ask, what is the energy? Like, what is energy?
Mm-hmm. Right.
If there's nothing, there's no energy. So energy is something that something possesses.
Mm-hmm.
There has to be something in order to have energy.
Right.
So where we see that equation work a lot is in a particle accelerator.
Right.
You collide protons and antiprotons, like in the Large Hadron Collider.
Mm-hmm.
So they're made out of quarks, and so two quark and an antiquark come together,
Mm-hmm.
annihilate each other. So they both had mass, annihilate each other. There's a bunch of energy,
Mm-hmm.
equal to what you get from Einstein's famous formula. But what is energy? Well, you have to have something in order for it to have energy.
Mm-hmm.
So they annihilate and they put out a quantum of light.
Mm-hmm.
Right? A very energetic quantum of light, and that quantum of light has that amount of energy. So you should think of it as the available energy,
Okay.
right? Because there's no such thing as energy without some object to possess that energy.
Sorry. How does string theory explain that? I think because in string theory, everything's that vibrating string, and it's just the different in vibration that determines if it's a particle or energy or different particle.
Well, it's just the same. It's just the same. A string and an anti-string can come together and annihilate and make some other thing, but there has to be something to contain the energy.
Right.
Right, and so it's yet a third kind of string with that much energy. It's basically the same. You simply replace the particles by strings.
Mm-hmm.
I think one of the beauties of string theory, way back at the beginning, the first string revolution, which I was around for, was the fact that it was a quantum gravity theory, which was already amazing.
Mm-hmm.
But more than that to be a quantum gravity theory, a whole bunch of things had to fit together just perfectly. A very intricate array of ideas had to mesh in just a perfect way.
Mm-hmm.
Right? So the string has excitations, which you interpret as particles. They look like particles.
Mm-hmm.
But it can get arbitrarily excited. So one string, in a sense, corresponds to an infinite tower of particles.
Okay.
Each sort of mode of vibration of the string is yet another particle, another particle. And the masses of those particles are, of course, bigger and bigger,
Mm-hmm.
because they, in a sense, have the energy you need to make that vibration, right?
Mm-hmm. Right.
But the tower of masses is tuned in just such a way that when you add up all their effects, when they interact with the gravitational field, you get a very nice theory of gravity that doesn't suffer from all these short distance problems that just naive quantization of Einstein's gravity would have.
Mm-hmm.
And it's just a sort of concert of this infinite number of particles somehow being excited. In some way, it gives a limit to the distance size of space-time.
Mm.
in that it doesn't really make sense to think about distances shorter than the characteristic size of a string. Because if you try to probe it, of course, what can you do? You can probe it with strings.
Mm-hmm.
Okay, so you can, with a higher and higher energy string, defeat the Heisenberg uncertainty principle and probe shorter and shorter distances until the energy gets enough that the string starts to get longer.
Oh, yeah.
And then with a long string, you again can't resolve short distances. So there becomes a minimum distance that you can resolve.
Mm.
And then the whole mathematics of string theory feeds that idea back on you. And it sort of makes even the question of what is space-time at a distance shorter than that a nonsensical one. It sort of doesn't exist at short distances.
Mm.
And this sort of solution of quantum gravity is very intricate. That was a real beauty. One of the selling beauties of string theory, I would say, that just a whole bunch of things had to fall together.
Mm-hmm.
You know, like a symphony of ideas all coming together at once.
Mm-hmm. So being that the string is extremely small, is it the size of a Planck length, or Planck length is even smaller than the string?
It's a little bigger, 10 times, 100 times.
Than Planck length?
Yeah, something like that.
Okay. Yeah, I heard somewhere that if you took an atom and you blew it up to the size of a solar system, the string would be the size of a tree.
I don't know. Could be.
That's tiny.
Could be. I'd be surprised if it's even that big, but yeah.
Yeah. Because you can't really see it in resolve it in a way. That's why you can't detect it, so it's very hard to prove, right?
Yes.
Yeah.
It's not just string theory, but gravity in the quantum regime itself.
Mm-hmm. Because gravity is so weak, right, on those tiny scales.
It's so weak, and it becomes quantum mechanical only at very high energy or short distance.
Mm-hmm.
So, for example, the electron, point particle. So it has a mass, so it gravitates, it attracts itself by gravity.
Mm-hmm.
Why isn't it a black hole? Right? It's small enough, extremely dense.
Mm-hmm.
And the reason is because quantum effects fuzz it out so that its fuzzy size is bigger than, it's big enough so its gravitational self-attraction doesn't make it collapse to a black hole.
Okay.
And in fact, the Planck mass, so to speak, is how heavy the electron would have to be to become a black hole.
Oh wow! I heard somewhere that in LHC there was this worry, or I'm not sure if it was founded by anything, but that maybe we'll be able to create a mini black hole with. But I think, did that ever happen? Or
no. Worries like that have been there. You'd be surprised at things people are worried about.
Mm-hmm.
And that was one of them. There were theories popular at the time, kind of brain world theories, so to speak, where gravity wasn't, where the scale of gravity wasn't so small.
Mm-hmm.
There was a way of, by making gravity spread out in an extra dimension, so somehow confining us to our three space dimensions at one time, but letting gravity spread out in another dimension. Mm-hmm. There was a way of making the scale of quantum gravity not much different from the other particle physics scales. And then if you did that, you could have things collapsing to black holes mm-hmm. at particle physics scales. Mm-hmm. So if you turn on a new accelerator, you might suddenly start producing black holes. And of course, if they were really tiny, they might evaporate by Hawking radiation and just go away.
Right.
But what if not? What if it started to grow and eat everything around?
So with the Hawking radiation, that's another thing I actually wanted to ask. It's it's a fascinating idea that the black hole sort of radiates the heat, right, or the energy out very slowly, but eventually what would happen, the black hole would sort of disappear over like trillions of years. But the question is, how can a black hole evaporate heat or evaporate anything? Like how can anything get out from the black hole if a black hole sucks everything in and nothing can escape?
Okay, it's a nice question. I think the Hawking idea was that you always in classical mechanics, nothing gets out. But in the quantum world, you have particles around, quantized particles.
Mm-hmm.
And then amongst quantized particles, there's always something happening. In a sense, the vacuum of space-time, the place where there's nothing, is actually quite an active place. Mm-hmm. There are always particle-antiparticle pairs being created and re-annihilated in a sense there. So then the Hawking idea is you have the event horizon, particle-antiparticle pair is created near it, one of them falls in and can't get out. Mm-hmm. And then they, in a sense, conserve the momentum, the other one gets kicked out and goes away as Hawking radiation.
Okay. It's on the event horizon somewhere there. Okay.
Yeah, so in some sense, the uncertainty in position of quantum particles defeats this idea that nothing can get out.
Mm-hmm. So something does get out.
In fact, if the event horizon is a drama-free place, you don't even know that you're there. Quantum uncertainty can put a particle partially in and partially out.
Mm-hmm. Okay.
Then what happens?
Right.
Does it fall in, or can it stay out, or is it in a superposition of states where it's in and out?
Mm-hmm. Okay. Yeah, that makes sense. Other thing, going back to E equals mc squared, if there's that equivalence between mass and energy, it's almost like you could say it's the same thing, really, in a way. And if mass can bend space-time and create gravity, does it mean that energy technically could do the same?
But remember, something has to have the energy. But in a sense, it could, although it depends a little bit. Right? Because you can give a particle a lot of energy just by speeding it up, making it go really, really fast. But that doesn't by itself bend space-time any more than it did when the particle's sitting still.
Right.
You have to have more going on than that.
Mm-hmm. So I guess if you had like a super powerful laser, more powerful than anything we have, and shot a beam through the universe, if that beam was powerful enough, it could, in theory, bend space-time around it, maybe.
In theory, yeah. In some sense, you want to concentrate energy, and you want it in a given place. Mm-hmm. So just taking something and giving it energy by speeding it up isn't good enough. Mm-hmm. You want it running beside it and looking at it, so you're still, compared to it, you want to be able to say it has a huge amount of energy. Mm-hmm. And then there can be gravitational collapse. Mm-hmm. Right. Space-time curvature and all that. But still, I think the event horizons of black holes, which are kind of indirectly known now to exist in the universe, I think their space-time is still very mildly curved. They should be just regular places. Mm-hmm. Even the strong tidal effects, which would tear you apart as you're falling into a black hole, wouldn't occur until you're way inside the event horizon.
There's that concept of that when you fall into a black hole, the gravitational force is stronger at your feet than your head. It's so you get spaghettified.
It's tidal forces will.
Oh, one more thing. 0-point energy. That's an interesting idea. Could you talk about that?
I say something that is very poorly understood in high energy physics, but measurable and clearly exists for atoms and things that are accessible and measurable. Why do I say poorly understood in particle physics? Well, it's because all of the particles in the standard model of particle physics should have a 0-point energy, which means this energy should be around. And if you take that energy for the known particles, even up to the known energies, that would be a huge dark energy which would collapse the universe to something the Planck size immediately. So for some reason, gravity doesn't see this 0-point energy of particles. And that's poorly understood. Why doesn't it? Mathematically, it's not that bad a thing. You can add a mathematical term to Einstein's equations and cancel it out and throw it away and then solve the equations and go away happy. But why Einstein's equations would be tuned like that with this extra term, which has to be fine-tuned to some incredible accuracy. I think it's also 1 in 100 decimal places or something like that. I don't remember exactly. Why they would have that term so finely tuned is a good question. Some physicists tend to worry about that question more than I do. I kind of think why nature chose one number over another not to be such a puzzle, because it had to choose some number. Right? It's like trying to explain why somebody won the lottery. Well, if you just look at that guy, it's extremely unlikely he's ever going to win the lottery. But if you look at the lottery, someone had to win.
Yeah.
Right? So there has to be an unlikely guy who won the lottery. So the same with this number you add to Einstein's equation. It's an unlikely number, very finely tuned, but that's the one that gives the world that we know.
Is it you're talking about cosmological constant?
Yeah, so that's a problem that I'd say there's a very poor understanding of, besides the fact that it isn't a real mathematical problem, that you can cancel it by adding your own cosmological constant with opposite sign in Einstein's equations.
Right. If you were to say a message to aspiring physicists or young people who are fascinated with physics and they want to go and study it, what would you say to them? If, being that you've been in this field for so many years and you have the wisdom, what would you tell them, what to do, what not to do, maybe?
Okay, that's a good question. In fact, I guess I do tell young people what to do quite often. I do tend to tailor it to the person a little bit, because of course everybody's a little different. But I would say if you have a physics education in front of you, try to get a broad education. The technical things might look challenging, might look like they're hard to learn, but eventually, if you need them, you learn them. It just takes some time. What's much harder is a broad point of view of all different sorts of phenomena in physics. That's quite a bit harder. People tend to get specialized. As you go on, you get more specialized, and I think the more creative people and perhaps more successful people tend to have a very broad point of view. Not that you might need the specific phenomena from some other field or even the specific techniques, but just the ideas.
Just be curious about the world you live in.
Yes,
Yeah.
just the ideas. A broad-based education is golden.
Right. When you think of all the geniuses in the world, like Da Vinci, for example, or they all had very broad interests, right? They're interested in biology, in history, in physics, and I think only when you know a lot of things from many different areas, you can aggregate this knowledge and create something really amazing. It's almost like there's a synergy between different domains. When you know a lot of things, every single one of those the domains you study is going to benefit from it.
Yeah, unfortunately, the Renaissance man doesn't exist anymore. I think the amount of knowledge is just too big. In fact, even in one field, like in mathematics, I've been told that the last mathematicians who knew everything in mathematics were 100 years ago. That it's simply impossible now. Maybe AI will change it.
Yeah, we're talking about the Renaissance man. So it's true that in today's world, with every discipline being so advanced, you can't really be an expert in every single one. But just, you don't have to be an expert, just have an idea of it. Like, you don't have to be a historian, but I think everyone should know sort of a brief history of the world, where we came from. We should know, have like an idea about how human body works, stuff like that. Some people are experts in one domain and they don't know anything about anything else. But like you said, I think it really helps if you have an understanding of the world.
I agree. An understanding of the world from a broad-based education, that's one thing, but a Da Vinci who basically knew everything about mathematics, physics, engineering, medicine, art, that's another level, and that doesn't look possible in the present day.
Yeah. Thank you so much. I really appreciate talking to you, and thank you for taking the time.
Okay, it was a real pleasure. Thank you.
Thank you.